Welcome back to CMOS radio frequency integrated circuits. We are in the 11th module, we are talking about frequency synthesis, and as part of the frequency synthesis procedure, in the previous lecture we were discussing how we can modify a phase lock loop and create something called an integer n frequency synthesizer. So, the small modification is a clock divider, which is readily available using digital circuits. So, that is the modification that we are going to make, and we are going to label this as an integer n frequency synthesizer. Now, some important points as far as the integer n frequency synthesizer is concerned. Number 1, the loop bandwidth is limited to a fraction of the reference frequency. It has nothing to do with the frequency that you are finally generating. It has everything to do with the rate at which the phase detector is operating. So, the speed at which the phase detector is operating, that is what is important over here, not the rest of the circuitry. That is going to tell you what is the maximum bandwidth you can have for the loop. Great. So, next we read a small exercise, and we saw that even when up and down, even at perfect lock between the reference and the divided output, even when these two are perfectly locked, up and down have small pulses of equal duration, right, and this happens because of the delay of the AND gate as well as the clear operation within the flip flop. Now, because up and down have these small glitches, and because it is impossible to perfectly match two current sources. Also note, one current source is a source, the other is a sink. Okay. So, they are not even of the same quality. So, one will be made with NMOSes, the other will be made with PMOSes. It is very hard to perfectly match an NMOS and a PMOS, it is not possible. There will be a small bit of error, right. So, with this small bit of error between the two current sources, because of these these errors in the current sources, and because of the finite delay, non-zero delay of the gate and the clear signal, you are going to get small glitches on the control voltage. Now, these glitches are going to appear periodically at a frequency of the reference frequency. That is the periodicity involved, which means that if I look at a plot of the spectrum of the control signal, then I will have a DC and I am going to have all of these tones. The fundamental is FREF, I will have FREF and all its harmonics in my control signal. Agreed? Now, notice over here, how can I reduce these tones? I can get rid of the tones by making the time, the delay equal to 0, okay, not possible. I can get rid of the tones by making delta I naught equal to 0, mismatch, not possible. I can get rid of the tones by increasing C plus Cx. Ooh. So, what I am saying over here is that why do not we increase C plus Cx? That is going to reduce the tones. What is going to happen if I increase C plus Cx? What is going to happen if I increase the capacitance? If I increase the capacitance, the RC product is going to increase, which means that the loop bandwidth is going to decrease. It is fairly simple. If I decrease the loop bandwidth, if I decrease the bandwidth of this particular filter, let us redraw it. Okay. So, this is my synthesizer, right. N is programmable. This is the integer n synthesizer. N is programmable. Let us say, let us take some numbers here. Let us say Vref is 1 megahertz. Let us say N is programmable between 900 and 1100. Okay. And let us say you have built the VCO to operate from 900 megahertz to 1.1 gigahertz. All right. So, if you do such a thing, then when n is 900, the output is going to be 900 megahertz. When n is 955, the output is going to be 955 megahertz. So, as and when the base station instructs you to go to a particular channel, you can go to that particular channel. The step size that you have got over here is 1 megahertz. So, the channel raster, the spacing between two channels is 1 megahertz that you have got over here. Why? Because you chose the reference as 1 megahertz. Very interesting, right. So, the reference has got to be the raster, the step size between the channels, spacing between the channels, that is the reference frequency. Then you can go to any arbitrary channel that you so desire. Okay. Now, let us come to the point. What I am saying is as follows, that there are glitches on up and down even when the circuit is locked, and there are mismatches between these two currents. Okay. As a result, some extra charge goes into the control node, and when the extra charge goes into the control node, what we are going to see is that the voltage is going to increase a little bit by this quantity. That is the extra charge that is going in, charge divided by the capacitance is the amount of voltage increase. All right. So, this is the problem, and what I am suggesting is increase C plus Cx, increase the capacitance. If I increase the capacitance, the loop bandwidth is going to drop. If the loop bandwidth drops, then effectively I am going to filter out this signal which is at fref. So, there is a signal coming in, think of it as a filter. Your input is the up and down signal, right. Your output is the control voltage. Okay. So, what I am suggesting is decrease the bandwidth of this filter. If I decrease the bandwidth of the filter by n times, then depending on the order of the filter I get that many number of decibels rejection. So, let us say if the bandwidth of the filter is f ref by 10, I get 20 dB reject, it is a first order filter. Is it a first? Yeah. Let us say you have got a first order system over here, bandwidth of the filter is f ref by 10. In that case, if my input is at f ref, that is where the input is, f ref and its harmonics, right. Then your output will have rejection of minus 20 dB. 20 dB per decade. At f ref, I am sorry, at f ref by 10 everything passes. So, what is going to happen at f ref? Going to get 20 dB lesser, right. What if I change this to f ref by 20? Then I am going to get 6 dB more improvement. Right. So, what I am suggesting over here, is that consistent? If I double the, if I half the bandwidth, that means I am doubling the capacitance. If I double the capacitance, then the size of these delta V's becomes half. So, it is the same phenomenon. So, it agrees. So, make the loop bandwidth smaller, you are going to get even better performance. You can get rid of these spurs completely. Unfortunately, as you make the loop bandwidth smaller and smaller, the VCO is going to mimic the reference within that loop bandwidth. So, that becomes a problem, phase noise becomes a problem. So, the output that you are going to see from the VCO, so suppose this is the free running VCO output and this is the output if I mimic the reference. How are you going to mimic the reference? What does it mean by mimicking the reference? The reference is at a different frequency. So, let us say n equal to 2. So, this is sorry. This is the crystal oscillator spectrum, okay, and twice this frequency is my VCO spectrum. Kind of exaggerating the view, I have put a lot of bad phase noise over there, it is okay. Now, the comparison is between the divided output. You divide the output by a factor of 2 and then compare each other. That is, you compare the reference to the divided output. So, when you divide this particular VCO output by a factor of 2, what does it mean? How is the spectrum going to look like? Any guesses? The spectrum is going to scale in the x axis by a factor of 2. So, this point will translate to this point by 2, this point will translate to this point by 2. Every point is going to translate to that point divided by a factor of 2. Okay? So, you are compressing the x axis by a factor of 2. So, this compressed version is probably going to look like this. I do not know, hopefully it is worse than the crystal oscillator, or I mean not hopefully it is worse than the crystal oscillator, it is going to be worse than the crystal oscillator. Crystal oscillator is beautiful. So, then the job of the loop is to make sure that when you divide it, the final the job of the loop is to make sure that the error signal between these two is equal to 0, which means that the divided spectrum is going to look like the reference spectrum. In other words, if you scale the x axis of the reference spectrum by a factor of n times, if you make it n times, then that is the expected spectrum at the output of the VCO. You get what I mean? So, if you multiply this by n times, just the x axis point by point, you are going to get the spectrum at the output. So, therefore, what I mean by saying that the output has got to mimic the reference is really not quite the statement, right. It is not exactly correct. The output has to mimic a scaled version of the reference. The x axis has to be scaled n times. So, if your reference looks like this, then you have to take point by point, scale it up, expand the x axis. Maybe this is how the output spectrum will look like. The scaled reference is going to look like. Now, what this means as far as our synthesizer is concerned is that within the loop bandwidth, remember the loop bandwidth is only this much. That is the strange part, right, that the loop bandwidth is only that much. So, within that loop bandwidth, the output is going to mimic the reference, and outside that loop bandwidth, it is going to behave exactly as if it were the normal VCO. So, our job is to make sure that this loop bandwidth is as large as possible, so that I can get rid of as much phase noise as possible. And then contrarily, we are saying that to reject the spurs as much as possible. So, there are some spurs over here. To reject the spurs as much as possible, I would like to keep the loop bandwidth as small as possible. Now, comes the engineering trade off. You have to figure out how much exactly loop bandwidth you are going to allow. Accordingly, you have to make a very good voltage controlled oscillator, so that you do not create too much extra phase noise. Accordingly, you can relax on the delay of the AND gate and of the flip flops, and on the mismatch between the push and up and down currents of the charge pump. So, these are the trade offs. What about settling time? Well, less loop bandwidth means automatically means that the settling time is going to be that much more. Too bad, right? So, if you want to improve spurs, performance of the spurious frequencies, if you want to reduce the spurious frequencies, then you have to have lower gate delays, you have to have better matching between the up and the down currents, you have to have lesser loop bandwidth. Unfortunately, if you want better phase noise, you need more loop bandwidth. If you want to have lower settling time, then you want to have more loop bandwidth. So, there are a lot of reasons why you want to have large loop bandwidth, and okay. So, there are a lot of reasons why you want more large loop bandwidth. So, either you have to live with the spurious frequencies, or you have to do a better job with the matching between the push and pull current, up and down current, and you have to have lower gate delays. The other possibility is a rethink. What if n is not an integer? Okay. Let us rethink. Let us say that here we divided by a number n, that was our architecture. What if I do not divide by an integer? I had restricted n to be an integer. I say that let us try to design a circuit which we'll make it in the future. Suppose I make a division, some sort of divider circuit which divides by non integers, by any number, okay, any real number. In that case, the reference oscillator does not have to be the channel spacing. Remember, the reference oscillator is the channel spacing in our integer n synthesizer, integer division. Reference oscillator is running at the channel spacing, which means that the loop bandwidth is a fraction of the channel spacing. Okay. And it also means that you are going to get spurious frequencies at the channel, at precisely the channel spacing, which means that at every channel you are going to get a spurious tone. It is ridiculous. you are going to kill everyone else. Okay. So, the suggestion is that what if I make n to be a non-integer. Okay, let us not think about the spurious tones now. If n is allowed to be not an integer, then the reference frequency does not have to be the channel spacing, right. Suppose I want to range between 900 megahertz and 1.1 gigahertz at a channel spacing of 1 megahertz, but I am allowed to do division by not only integers, but 1/10 of integers also. So, I can do division by 990.1, I can do division by 90.2 and so on and so forth. In that case, my Vref could be 10 megahertz. So, think about this, right. So, if I am able to divide by k, where 10k is number integer between 900 and 1100. Okay. I mean, this is just a thought, right. This might not be what you are going to do, but this is just a thought. So, I am allowed to divide by 90, I am allowed to divide by 90.1, k can be 90, k can be 90.1, k can be 100.5, k can be 102, k can be 102.1, k can be 110. Okay, will this work? Will it work better than before? Why can it work better than before? It can work better than before for the simple reason that now the loop bandwidth maximum loop bandwidth is going to be a fraction of 10 megahertz. So, earlier my loop bandwidth was a fraction of 1 megahertz. In this case, I have managed to increase my loop bandwidth 10 times. Isn't that nice? Why is it nice? Because now I can improve my performance as far as phase noise is concerned. I can improve my performance as far as settling time is concerned. I can settle faster. I can have my oscillator will have lower requirements as far as phase noise is concerned. I will not have to worry about phase noise right next to my oscillation frequency, right. So, it will mimic the output of the synthesizer will mimic the reference with a larger bandwidth, 10 times larger bandwidth, and that is a lot as far as I am concerned. That means a lot to me. Okay. We looked at the importance of phase noise earlier on. when we were working on mixers, right. So, the VCO phase noise is going to be irrelevant within that loop bandwidth. Outside the loop bandwidth, of course, the VCO should have good phase noise performance, right. So, is this a better approach? What do you think? Now, we can't really say what this is going to do as far as spurious frequencies are concerned, right. So, that is question mark, because we do not know what this signal looks like. We do not exactly know what this signal looks like. It's most probably not going to look exactly like 10 megahertz. If it does look exactly like 10 megahertz, then is there a problem? There is no problem as far as the spurious tones are concerned. The spurious tones will start appearing at 10 megahertz apart instead of 1 megahertz apart, right. So, that is clear. So, if this is also a 10 megahertz signal, may or may not be, it all depends on how I do this division. So, supposing it also looks like a perfect 10 megahertz signal, in that case the spurious tones will appear at a spacing of 10 megahertz. And since my loop bandwidth is 1 megahertz, 10 megahertz will have the same 20 dB rejection as before, right. Here whatever I was getting at 1 megahertz, I will get the same tone, but at 10 megahertz. So, in that sense also this is kind of better, seems to be better. Okay. So, this is all neat, only stumbling block is this business. How can you possibly divide a frequency by a non-integer? Okay. So, our traditional digital circuits, I can make a counter which with my flip flops and so on. This is what we had done to make the division, right, and this is kind of not going to work with non-integers. So, this is a problem. How are we going to make this division by k? So, everything is fine in theory. On paper it looks like this is going to perform better. It is definitely going to perform better in terms of phase noise, it is definitely going to perform better in terms of settling time. Performance in terms of spurs, it looks like it is going to be better on paper, we will have to examine that. Only question mark over here is what is inside this division by k. Okay. So, let us try to divide by a non-integer, and as an example let us try to do the following. Let us say that I have got a clock running at 1 hertz. Okay. And I am going to follow this algorithm that every 2 clock cycles I am going to divide by 2. So, for 2 clock cycles I am going to divide by 2, and for 3 clock cycles, I am going to divide by 3. Okay. It's a funny kind of situation. 2 clock cycles I am going to divide by 2. So, from here to here I am going to divide by 2, and the next 3 clock cycles I am going to divide by 3. Again for 2 clock cycles I am going to divide by 2, and for the next 3 clock cycles I am going to divide by 3. What is the output of this going to look like? The output is going to look like this. So, I have divided by 2 for 2 clock cycles, and then I want to divide by 3 for 3 clock cycles. And this is going to be periodic. This is going to keep repeating itself. It is going to keep repeating itself at what rate? What is the total period of this? This is the total period of this, 5 seconds, right. It is going to keep repeating every 5 seconds. Okay. Now, what does this look like as far as the phase detector is concerned? Does this look like a signal which has a period of 2.5 seconds? Or rather, as far as the phase detector is concerned, do you think you have successfully divided by 2.5? Divide by 2.5 means a period of 2.5 seconds. Well, on the average, it is like this. You have got 5 seconds. In 5 seconds, you have got 2 cycles. You have got 2 up and down. You have got 2 cycles going up and going down. And the average cycle seems to be lasting for 2.5 seconds. Is that not so? That is right. The average cycle seems to be lasting for 2.5 seconds, which means that it looks like you have successfully divided your whatever was coming from the VCO by 2.5. So, looks interesting, right? Now, let us say that the reference was at 2.5, 1 by 2.5 hertz, which is 0.4 hertz. So, okay. So, this is 1, it needs to go high at 1.25, right, then low at 2.5, then it is going to go high at 3.75, a little before this comes, then low at the right point, and then again this is going to okay. So, this is let us say the reference. Okay. Now, if this is the reference, then let us examine what our phase detector is going to do. We are going to use the same phase detector, right. Now, the output of the phase detector is going to do the following. First, the edge of V out by 2.5 comes. So, it is going to give you a down pulse. Then the edge of V ref comes, things are going to stabilize. So, this is for a quarter of a second. Right. Then after a long time, the reference goes up first, then quarter of a second later it stabilizes. Then again there is a down pulse for a quarter of a second, and no, that is right, there is a down pulse for a quarter of a second. I think there is a alignment problem here, this should have been an up pulse for another quarter of a second. This is going to be the output of my phase detector. Now, this looks brilliant, does not it? Up and down of equal durations, different points of time of course. This is beautiful, is not it? It is very nice, which means if everything is perfect, then things are going to, nothing is going to change as far as the control voltage is concerned. If nothing changes as far as the control voltage is concerned, then the output of the VCO does not change, which means you have got lock. So, you have successfully divided by 2.5. Now, if I can do 2.5, I can do any other fraction, I just have to spend some time on it, right. So, this is something which is very, very interesting, is not it? What is the periodicity of this pulse? So, without any loss of generality, if I can do 2.5, I can do other numbers as well. This is basically the strategy I am going to follow, right. We now have a technique to do this division. Next question is, what does this mean as far as the spurs are concerned? We think that the spurs are going to be at the reference frequency, is that correct? The reference frequency is 1 by 2.5 hertz. Are the spurs coming at 1 by 2.5 hertz or at some other frequency? what is the periodicity in the phase detector output? What is the period? The period is the net period, which happens to be 5 seconds in our case. Five seconds means that we are really getting spurs at 1/5 of a hertz, 0.2 hertz, not 0.4 hertz. All right. So, this is the story. So, the spurs are not going to be coming at 10 megahertz. The spurs are not coming at the reference frequency. Here the reference frequency was 0.4 hertz, okay, but the spurs, as far as I am concerned, are coming at 0.2 hertz, an even slower rate. The periodicity in the spurs is lesser, the period is more. So, the spurs are not going to come at 10 megahertz, the spurs are going to come at a fraction of 10 megahertz. All right. Now, as far as my loop bandwidth is concerned, I have made my loop bandwidth equal to 1 megahertz or so. Spurs are coming at 1 megahertz, let us say. In that case, the spurs are going to go right through. It is a problem. Spurs are almost within my loop bandwidth. In fact, they are going to be within the loop bandwidth for larger ratios, for larger deeper fractions, for example. Now, okay, fine. So, the understanding is, first let us try to understand how we did this magical division by 2.5. How did we do the division by 2.5? We took two periods, 2 cycles, during which I divided by 2, and I took the next 3 cycles and divided by 3. Okay. So, over 5 cycles, I have done my job over 5 cycles, and for some of these 5 cycles I have divided by 2, some of these 5 cycles I have divided by 3. Let us try to generalize. Let us say that I take a lot of these cycles, and for some cycles I divide by n, and for some other cycles I divide by n plus 1. Let us call them k cycles and m cycles. So, for k cycles I am going to divide by capital N, for m subsequent cycles I am going to divide by capital N plus 1. It is feasible to do this with digital circuits, right. So, let us say the output has a period of p out. So, the total time during which I am doing my experiment is k times p out plus m times p out. Okay. So, this is the total period during which I am doing my experiment, right. And of course, m plus k times p out is going to be the net period. Okay. And if this is the net period, then the spurs are going to appear at 1 by this. So, fundamental for spurs 1 by m plus k times P out is F out. Okay. Now, what is this fraction by which we have managed to divide by? Let us try to understand what this fraction is. K clearly has got to be a multiple of n, and m clearly has got to be a multiple of n plus 1. Okay. So, k number of cycles has to be something times n, otherwise you can't divide by n nicely, and m cycles you want to divide that by n plus 1. So, that also has to be some multiple of n plus 1. Okay. Otherwise, your division is not really quite going to work out. So, that means that this is equal to fine, that is the net period that I have got. Now, over this net period, over the duration of the net period, how many cycles, how many times is the divided voltage going up and down? That is the question. So, as long as I am dividing by n, I am dividing k cycles by n. So, it is going to go up and down a times during that division, and it is going to go up and down b times while I am dividing by n plus 1. So, the output of this clock divider is going up and down a plus b times over the duration of the net period. Which means that the average period or rather the reference period has got to be equal to this net period divided by a plus b. Okay. Net period is equal to a n plus b n plus 1 whole thing times p out. So, that means that the frequency at the output of the divided is 1 by the period times right, and 1 by P out is basically equal to F out. So, the quantity by which you have done your division is this A n plus b times n plus 1 divided by A plus b. Now, does this work out as far as our example was concerned? We said that we have done a division by 2.5. Is that equal to 1 cycle times n it is, right. So, therefore, this formulation is correct. This is a way of checking whether what the work I have done, whether it is correct or not. And basically, now you choose your n, you choose your n plus 1, you choose a and b, and you can get different kinds of fractions as far as you are concerned. All right. So, we are going to summarize here, we are going to get into more details as far as this division is concerned in the next class. This technique is called the fractional n frequency synthesis. Okay. So, I am giving you the name after doing the whole thing. Let us stop over here and we are going to carry on in the next lecture. Thank you.